We're going to start, actually the verbiage that's up here, just kind of walk through this quickly before we get to example 1. So we've been looking at the integral. All right, so this is the integral here. We've been looking at the area underneath the curve being f of x. So integral is going to find how much area there is between point A and point B between the curve and the x-axis. And the fundamental theorem of calculus says you can do that by looking at the parent function, capital F here, and using the parent function to figure out where did I start minus where did I finish, right? Fundamental theorem of calculus. To help us think about that, we have been looking at this as a problem involving velocity. So if you think about this as velocity, so you're looking for the integral between point A and point B of this velocity function. Well, the parent function for velocity is position. So if you're just simply asking yourself, where did I start minus where did I finish, and that'll give me the total distance that I traveled, which is what the area underneath the velocity curve is. So today we're going to look at it in these notes, we're going to look at it from a slightly different perspective. It's the same exact math, it's just got different names to it, different vocabulary, and that different vocabulary is going to allow us to answer some different questions, kind of questions you will see on the AP exam. So we've just simply taken right here fundamental theorem of calculus and written it with different vocabulary, and we're looking at this function f of x, and if we want to find the integral of the derivative function, the integral from a to b of the derivative function, well, we go look at the parent function. Well, if the derivative function is this, f prime x, then the parent function is just simply the f function. So we're looking for how far did we go if our endpoint was b and our starting point was a. Right? So it doesn't seem terribly profound at the moment. The first example will also not seem terribly profound. As we get into this, you'll hopefully see why we're bothering. All right, so example 1. Suppose we have this function and we know that its derivative is 3x squared plus 6, and we know that f of 2 is 10. So when the function, unknown function at the moment, when we plug in x is 2, we get a value of 10. I'm going to skip over a for a second. We're going to do b, because b is probably the way that you would do this problem if we weren't doing these notes. If I just simply gave you example 1, this is how you might do this problem. Right? So you would say to yourself, well, if I know that the derivative is 3x squared plus 6, well, then I can take the antiderivative of that. Right? So do this here. So if I know that, oops, wrong pen. Excuse me. If I know, having trouble with my software here. Hold on. Try this. Alright, we ready? There we go. If I know that the derivative is 3x squared plus 6, well, then that means that the antiderivative, the function itself, must be x cubed plus 6x plus some c. And I've been given the fact that f of 2 is equal to 10, and if f of 2 is equal to 10, then I know that when I have Actually, we'll do it this way. I know that 2 cubed plus 6 times 2 plus some unknown c is equal to 10. And then if I solve this, I'm going to get 8 plus 12 plus some c is equal to 10. And we find out that c must be equal to negative 10. And then if c is equal to negative 10, then we now know what f of x is, right? So f of x is equal to x cubed plus 6x plus negative 10. And if we're looking for, which we are because it says so right here, if we're looking for the function at 5, we just simply plug in 5 into this equation, do the math, and we get an answer of 145. Right? So that's kind of a logical algebraic way to do it. Right? So now we're going to go back and we're going to do part A up here, and we're going to use the integral to help us compute f of 5. Right? So this is the way that we're going to do that. We're going to start with what we know. Right? So we have the integral from 2 to 5 of this function, 3x squared plus 6 dx. And if we do this out, we will get x cubed plus 6x from 2 to 5, which is equal to, oops, that's not a 5. That's a 5, which is equal to 5 cubed plus 6 times 5 minus 2 cubed plus 6 times 2, which is equal to 125 plus 30, 125 plus 30 minus 8 plus 12, which is equal to 135. Right. So we have seen this before, where we can compute the antiderivative without having to figure out what c is. And remember, just as a side note here, remember the reason for that is that tucked into this part of the equation, right in here, there's a plus c, right? So that's the when we take the indefinite integral, or otherwise the antiderivative, we're always careful to do the plus c's, but when we're taking the definite integral, when we're going from between two defined endpoints, well, here we have the plus c, and then we're subtracting the plus c here, so the c's just drop out. So we can find the value of the integral without ever knowing where the parent function is up and down on the y-axis. So in other words, without ever calculating what the c value is. Alright, so now the question is, how does this integral help us find this here? Well, using the fundamental theorem of calculus, we know that the integral from 2 to 5 of 3x squared plus 6 dx is equal to the parent function, And so if this is f prime of x, the parent function is f of x. So it's equal to f of 5 minus f of 2. And we just calculated this integral. We found out that that was 135. F of 5, we don't know. That's what we're looking for, right? So f of 5. But we have been given, and it's just tucked up here right above the top of the screen, we have been given this value here. We know what f of 2 is. So then we can plug that in to the first fundamental theorem of calculus. This is 10. So then if we know what the integral is and we know where we were to end, then we can figure out where we were to start. So hopefully you can see that this then gives us the value that where we started, f of 5 is equal to 145. 45 that we calculated using the value of the integral is the same as the 145 that we calculated by doing it out algebraically. All right, so now let's see how example 2 is a place where we will end up where this new way of looking at or using the fundamental theorem of calculus will help us out of a bind. All right, what's the bind? Well, here is our function that we are interested in. Or actually, yeah, this is the function that we're interested in. We're interested in finding f of 3 if we know that its derivative is this, cosine x squared minus 1. All right. So if we're doing this algebraically, what we would do is we would figure out what f of x was. We would simply take the antiderivative of cosine x squared. All right. So let's give that a shot, see what we can do with that. So if we're looking for the antiderivative, that's attempt number 1. Perhaps f of x, well, if the sine, and we know that it's going to need to have been the sine of x squared, and then we have this minus 1 term here, so this must have been a minus x. So this is seems like a reasonable guess, and to check this, we'll just simply take its derivative. Right? So if we're guessing that the original function, the parent function, is sine x squared minus x, so let's see what its derivative would give us. Right? So we'll just check to see whether or not this works. Well, the derivative of sine x squared is indeed cosine x squared, but then we have to use the chain rule because we have this inside function, so we would need to take the derivative of x squared, which is going to give us 2x, and then the second term here, minus x, its derivative would be minus 1, and we have this 2x here tucked in our derivative that's not here. All right, so that didn't work. Don't like that. We could try and see if we could get rid of this 2x, anticipate this 2x that's going to result from the chain rule. So we could try this. We could say, well, perhaps the function is 1 over 2x times all of this that we had over here. Right? So actually, let me rewrite this slightly differently. We would get sine of the quantity x squared minus x all over 2x. And then to check it, we would take the derivative of that. So if that really was our parent function, and when we take the derivative, we end up then needing to do, oh boy, the quotient rule. So the derivative of the first times the second minus derivative of the second times the first. And that's not going to give us what we're looking for, right? If you want to try that out, it gets to be quite complicated, but because of the quotient rule, it doesn't get anywhere close to being what we want. So at this point, hopefully you see that we're not having much luck finding the antiderivative. All right. Do not completely despair, because when we get into Unit 7 or in Unit 8, we will start looking at taking antiderivatives of compositions, right? So this is a composition function, one function inside another. But even if we can't find its antiderivative, we can answer the question of, where is f of x? For example, if we wanted to know where the function is at 8. Right? So here's how we do this. We're going to first use the calculator to find f of 8. So all right, hold on one second here.